Good morning and welcome to Saturday of week 2 of your Physics 5 a day. And in this first video today, we're thinking about the normal contact force. When two surfaces are touching each other and pressing against each other, each surface exerts a normal contact force on the other surface. Now, normal here doesn't mean not strange. It's the maths meaning of normal. In maths, normal means perpendicular or 90 degrees. So this is a contact force that acts at 90 degrees to the surface that's exerting it. So here's the normal contact force exerted by the ground on the block, and by Newton's third law, the block exerts a normal contact force of the same size downwards on the surface. The 90 degree part of this is more obvious when you've got an object on a slope. So here, the force on the block is in that direction, still 90 degrees to the surface exerting it, and the block exerts a normal contact force in this direction, 90 degrees to its bottom surface there. Okay, but what causes it? Well, you can think of the normal contact force as being the force that a surface exerts on an object that's trying to push through it. So, for example, right now, my pen, you can think of it as trying to fall, or gravity is trying to pull my pen down through the table. And so the table exerts a normal contact force upwards on the pen, preventing it from doing that. The same surface will exert different sized normal contact forces on different objects. It depends on how hard the object is pushing down on the surface. So let's say that this stage is exerting a 400 Newton normal contact force upwards on the child. Well, it's going to exert a bigger normal contact force upwards on the adult, because the adult is pushing down harder on the table because the earth is pulling the adult down more. Is there a limit to how big a normal contact force the surface can exert? Yes. Chances are if I put an elephant on the stage, it would break. We can measure normal contact forces using an electronic balance, which is what in everyday language we call weighing scales. So here I've put a block on the weighing scales, and the block will be exerting a normal contact force downwards on the scales, and the scales will be exerting a normal contact force upwards on the block, and it's this normal contact force that the scale reading is telling us. Now, you may have thought that weighing scales were measuring weight, and the reading will be the size of the weight force, but that's only because the block is stationary and therefore in equilibrium. And so the normal contact force is the same size as the weight force. So it will tell us the size of the weight force, but it's not because it's actually measuring weight. We can't measure weight. It's the pull of the Earth's gravity down on us. We don't have any access to that. This is just like when you measure weight with a Newton meter. Again, many people think that when you hang an object from a Newton meter, it's measuring weight. It isn't. It's measuring tension force. You've stretched a spring inside the Newton meter, and so it's a tension force that it's reading. But the size of that tension force is equal to the size of the weight force, again because that block is stationary, and so these two forces have to be the same size. If you're not 100% convinced by this, go and get your bathroom scales and stand on them and stand still, and the reading will be your weight. And then bend your knees really slowly and try and watch the reading on the scales, and then jump. And while you're jumping, you're pushing downwards on the ground. You need to accelerate yourself upwards. So you're pushing down on the ground more than normal, and so the reading will be bigger than your weight. If the scales were measuring weight, they couldn't do that. But they're not. They're measuring normal contact force. The last thing to make clear on weighing scales is that, of course, when you stand on your bathroom scales, it'll actually say kilograms or another unit of mass there. but that's just because it's calibrated to measure the normal contact force and then divide by 9.81 to give you your mass. And the last thing to say about the normal contact force is its connection to feeling lighter or heavier or weightless. If this is you, you're the block. If this is you, there's your weight downwards. There's the normal contact force exerted by the floor upwards. And usually, because you're stationary and therefore not accelerating, usually these two forces are the same size. And so you can't feel weight. You can't feel the Earth's pull on you. It's a non-contact force. You've got no way to feel it. But you can feel the ground's upwards push on you, the N. And so actually the N is your experience of weight. What you think of as your weight, what that feels like, it is actually the N, the normal contact force on you. And you're used to this, you know what this feels like. So if you go on a roller coaster, when you're going over the top of a peak, for reasons that we'll cover in circular motion, the N force on you has got smaller, and so you feel lighter. You're not lighter, your weight force is the same size, but you feel lighter because the N force on you has got smaller. And similarly, when you go round a dip nice and fast, your weight hasn't actually changed size, but you feel much heavier because, for reasons we're covering in circular motion, the N force on you has got much bigger there. So weightlessness, what we call weightlessness, is actually when there's no N on you at all. And that, of course, is when you're in free fall. So if you jump out of a plane, we're going to imagine there's no air resistance as well. If you jump out of a plane, no air resistance, the only force acting on you is your weight, no normal contact force, and that's when you feel completely weightless.